Okay, I'm going to be working the 4.3 homework here, quadratic functions and their graphs. And this first one looks like quite a bit of work here. Let me just double check something. Okay, so what we have to do is drag these to the appropriate function here. So we have to inspect the function, see what its graph looks like, and then drag them in here. So that really could turn into where we're having to graph each of these, all 8 of them, using the techniques in class. Now I'm going to go a little bit faster here by looking at the ones that I can recognize with transformations from the previous section. So for example, this one here, x squared minus 1. X squared by itself, we know is a parabola. We know it looks like this. And then having a minus 1 there just moves the whole graph down 1. So looking at these graphs, looks like this one. Let me zoom in on this a little bit. And yeah, that looks like it right there. So I'm going to just drag that one here. And then let's see. This one here looks like a parabola because it has a negative in front of the x squared. That means it reflects it over the x-axis, so it opens down. And then down 2 means move the whole thing down 2. So it should look like that, which looks like this one. Let's see. Yeah, that looks like it's been moved down 2. So that one should go here. Okay, now for the others, let me take a look at that first one there. The first one is x squared minus 2x plus 1. So for that function, I know it opens up. If I try and get the vertex, I'm going to take this number here, that's b. So I'm going to do, find the h, I do negative b over 2a. So this will be 2 over 2 times 1, because a is 1. And that will be 1. And then to get k, I plug 1 into that function. If I plug 1 into this, I get 1 minus 2 plus 1. And that should be 0. All right, if I find a quick sketch, my vertex is at 1, 0, which is here. And it opens up. I only have one X-intercept and it's at 1, 0. And I can already tell from these pictures that it's got to be this one right here. Right there. So that one goes here. All right, the next one is f of x equals x squared plus 2x. So it opens up, I know that. The vertex, I'm going to do h, which is negative b. B is 2. A is 1, so over 2 times a, it gives me negative 1. If I plug negative 1 into that function, I get negative 1 squared plus 2 times negative 1. That gives me 1 minus 2, which is negative 1. So I have a vertex of negative 1, negative 1, and it opens up. Let's see, maybe I can tell from this right now. Negative 1, negative 1. I don't see that vertex anywhere. Is it? I don't see it. Oh, wait, this looks like it. Sorry. Yeah, negative 1, negative 1 opens up. I could go find these X-intercepts, but I think I can just do this one because it's the only one that has that vertex. So I'm going to go ahead and drop that one there. Okay, the next one is f of x equals x squared plus 2x plus 1. Okay, it opens up. I know that the vertex is going to be h is negative 2 over 2 times 1. That gives me negative 1. And if I plug negative 1 into the function, I get negative 1 squared plus 2 times negative 1 plus 1. So this is 1 minus 2 plus 1. This should give me 0. So I have a vertex of -1, 0. And looking at here, this one right here, -1, 0 is the vertex. Hard to see it there, but that looks like the only one it could be. -1, 0, yeah, let's go with that. All right, now the next one, f of x equals x squared minus 2x. Opens up. Okay, the vertex of this is h is going to be 2 over 2 times 1. So that gives me just 1. And then if I plug in 1 into the function, I get 1 squared minus 2 times 1. That's going to give me -1. So 1, -1 is the vertex. Let's see. It looks like this one. 1, -1. Yeah. So that's got to be this one here. All right, the next one. We have f of x is x squared plus 2x plus 2. Let's just go straight to the vertex. We know it opens up. So -2 over 2 times 1, that's -1. Plug that into the function. We get -1 squared plus 2 times -1 plus 2. So we get 1 minus 2 plus 2, which gives us 1. So we have a vertex of -1, 1. And that looks like this one right here, -1, 1 is the vertex. So that goes here, and that must go there. Let's check it out. Okay, I hope the next one's not like that too. Oh my goodness. Oh boy. Okay, this is gonna be a lot. Let's see, which ones can we do easily? This is a parabola that's been moved down 5, so that's got to be this one. It's just been moved down 5. This one has been reflected over and moved down 3. So that should be this one. And then for the rest of these, I'm going to try something. Wondering if I should maybe do. This is so similar to the last problem. So similar. Okay, so you can do this exactly the way the previous problem went, but I'm going to do something a little bit different to see if maybe just kind of give you a different feel for a way you can do this. Let's just take this first one. Forget, I'll just do the vertex. So the vertex, the h, I'm just going straight to vertex, should be 2 over 2 times 1, which is 1. If I plug 1 into the function, I get 1 minus 2 plus 2, so you get 1. So vertex of 1, 1 is this one here. I think this is too monotonous. I think you understand it from the previous one, so I'm just going to move on. There we go. So here it shows the answers if you want to see what each one was there. There it is. I think that's just too similar for me to work through all those problems again. So how do I go to the next question? This one, question 3. Oh my gosh, again. These are all the same. Okay, well. Okay, yeah, let's get to something different. Okay. So for the quadratic function, determine whether graph opens up or down. Okay, so does it open up or down? No, it's up. Check. Okay. What are the vertex? So we need to find the vertex of this. Again, we've done this enough. H should be, let's see, -b would be 2 over 2 times a, which is 1. So we get 1. Plug 1 into the function. This should give us 1 minus 2 minus 3, which is going to be -4. And so we get a vertex of 1, -4. So I write it as an ordered pair, 1, -4. Okay, axis of symmetry. We didn't talk about, well, we talked about, we didn't talk about the equation of the axis of symmetry. So the equation of the axis of symmetry is very simple, all right? Remember, the axis of symmetry is a dotted line, vertical line that goes through the vertex, right? So remember, vertical lines have an equation of x equals some number, right? Well, if it goes through the vertex, and our vertex has the coordinates 1, -4, then whatever the x coordinate is also the equation of this line, because that tells us, the x coordinate tells us our left and our right. So the equation is simply just h, x equals h, will always be the axis of symmetry equation. So x equals 1. Okay, what are the x-intercepts? Okay, so for this problem, it opens up our vertex. We would do a quick sketch, right? It opens up, the vertex is to the right 1, down 4, so it's here. So we know we have 2. So we would go find it by setting the function equal to 0. And for this, you either factor or you use quadratic formula. I'm going to factor because it does factor. I set each of these factors to 0, and I get 2 solutions, 3 and -1. So let's see how they want these. Comma to separate the answers. So let's try this. X-intercepts. I'm wondering if they want them as points. I think they do. Let's go with 3, 0. That's the first point. And then the other one is -1, 0. So 2 points. Maybe they just want the x coordinates. 3, -1. Yeah, okay, that's what they want. Okay, the y-intercept, all we do is plug 0 into the function. And if it's in standard form, then it's going to be easy. It's just -3. And clear this out. Let's see, they want us to graph this. All right, so we have a parabola, right? We have a vertex of 1, -4. So you can see up in the top right corner, it shows where we were right here. So 1, -4 right there. And then I'm going to go grab one of the x-intercepts was 3. So if I just move, you can see again, the top right corner, it shows right here what point you're about to drag to. So I want to drag it to 3, 0. That's one of my x-intercepts. It's like that. That should be it. Check it. Okay. Domain and range. So domain is all real numbers, so it's everything. We know this about quadratic functions already. Oops. Come on, what is going on? All right, and now the range is the y value. So we actually go from -4 up forever. So I need to include -4. So bracket -4, to infinity. Oh, it didn't take it. Oh, I have caps lock. That's why. There we go. -4 to infinity. All right. So we didn't do this in class, but I told you we would need to do it. So where is the function increasing and decreasing? So if you look at this function, it's increasing, going up. Remember, as you read from left to right, it's going up over here, right? And that happens starting here at the vertex x coordinate, which was at 1. So from 1 to infinity, it's going up, and it's going down over here from -infinity to 1. So it's increasing from 1 to infinity, and it's decreasing on the interval -infinity to 1. All right, this is the same question. I'm really going to start to cut back if I don't have to work through every single problem. These are the same type of thing, so I think you can handle that. This one's a little bit messy. I might do this one. I might come back and do that one. Yeah, that one, I think we might do. That one, I think you can do. up, down. Yeah, these are all pretty much the same. All right, so for this one, I think this one's worth us doing for sure right now. So it says determine the function whose graph is given below. So they give you a graph, right? So we did not talk about how to do this. This is actually a really good problem. So here's the thing. We've got this graph, right? And we can tell by looking at the graph that this is our vertex, right? Now, what we know about quadratic functions is that the standard form and the vertex form are two different types of forms, right? But the vertex form is really good if we have the vertex. So this is the form I want to use. I know that h is -2 and k is 5. So right now, here's what I know about the function. If I plug in -2 for h, so if I replace that with -2, it becomes x minus -2, which is x plus 2 squared, and then the k is 5, so plus 5. So here's what I know about this function so far. It must look like this. The only thing I don't know is what a is. But they give me one additional point on the graph. They give me the point 0, 1. And so what this means is when I plug in 0 for x, this is what the function should spit out. So what I'm going to do is I'm going to say, okay, well, if I replace this with 0, right, then my equation looks like this: a times 0 plus 2 squared plus 5. I know that when I do that, it must spit out the y value of 1. So now I can solve this equation for a, because this equation only has a in it. So I put a here. This is 2. 2 squared is 4, so times 4 plus 5. And so that just really means 1 equals 4a plus 5. I will subtract 5 on both sides, which gives me -4 equals 4a. And then I'll divide both sides by 4, and I get -1 equals a. So now I know what a is. So my final function is a, which is -1, and then x plus 2 squared plus 5. This should be the function that corresponds to this graph. So let's type that expression in here. Here we go. So -1, and then x plus 2 squared plus 5. Let's see if it takes that. Yeah. Okay. How many more do we have? I thought there was only 11. Okay, let's keep going here. Let's look at 12. Okay, so for this one, determine the quadratic function whose graph is given. So again, here we go. We have a vertex and a point. So this is the exact same thing, but I'll run through it one more time. So we know that the function must look like f of x equals a times x minus h squared plus k. I know that h is 2 and k is -3. So that tells me that this has to look like a, let's see, x minus 2 squared plus k, but k is -3. So that's what I know so far. But then this point here, 3, -1, means when I plug in 3 for x, my function spits out -1. So now what I do is I replace the x with 3. So we get 3 minus 2 squared minus 3 with an a in front. When I plug that in, it must spit out the number -1. And so now I just figure out what a is. So 3 minus 2 is 1, and 1 squared is 1. So this is times 1 minus 3. And I'll just add 3 to both sides, and I'll get 2 equals a. So a is 2. So now I know back up here that that had to be a 2, and that should give me the entire function. So let's type it in. It's 2 parentheses x minus 2 that squared minus 3. All right. Okay, a quadratic function f of x. So when you're given a quadratic function in standard form, and then this is saying that in the quadratic formula, the thing underneath the root is positive. So is basically saying that this thing has two solutions, or at least one or two solutions. So as long as you're in standard form, you have two solutions, then you can always rewrite the function this way, where R1, R2, the x-intercepts. In other words, it's just saying you can graph a function. I'm sorry, not graph, you can factor a function as long as it has one or two x-intercepts. So, okay, what does that mean? Find a quadratic function whose x-intercepts are given, with a being 1, 2, -2, and 4. So, all right, this is not as complicated as it looks. So we know that if a function can be factored, it can be rewritten as a times x minus R1 times x minus R2, where these R1 and R2 are the intercepts of the function. So first, they want us to figure out what the function would look like if the x-intercepts were -4 and 2. Okay, so and let's start with a being 1. Okay, that's what they have here. So if a is 1, it's 1. Okay, and then now x minus R1. Now R1 they're saying is -4. And then the other one is x minus R2, which is the other x-intercept, which is 2. And then that that minus becomes +4, and then over here x minus 2. So that's what a function that has these x-intercepts and a of 1 must look like. So let's type that in. I don't need the 1, but I'm going to put it there. X plus 4 times x minus 2. There we go. Wow, that's incorrect. What the heck? Do they want us to expand it? Maybe they want us to multiply this out. Okay, let's do that. Let's get rid of the 1. Oh, well, it doesn't say in standard form. I don't know. Well, let's see what it wants. Does it want it in standard form? What the heck? Yeah, they just wanted us to multiply this out. Okay, so they just wanted us to FOIL this, right? It didn't say that though, so I don't understand why that was counted wrong. So the only difference is if on this next part is if a is 2, then what we would do is we would take the same thing and replace this with a 2. So let me multiply this out. This is 2 times x plus 4 times x minus 2. So I FOIL this, that's x squared minus 2x plus 4x minus 8. But then I have a 2 in front. So 2 times x squared plus 2x, combining those two together, minus 8. Distribute that 2 through, and you should get 2x squared plus 4x minus 16. So all I did was distributed that 2. So the next one says, what if a was -2? Well, then we put a -2 here and distribute a -2 through. So I think you can realize that that's just going to change these things to negatives. -2x squared minus 4x plus 16. And then the last is, what if this was a 4? So if this right here had been a 4, right, all through here, then we distribute a 4 through, and that would give us 4x squared plus 8x minus 32. All right, next part. How does the value of a affect the intercepts? Well, they don't. You can change a all you want. The x-intercepts are always stay the same. Does not, but it changes the y-intercepts. There, doesn't affect them. Well, you change, it does not change things. It does not affect the y-intercept. No, it's got to be a. It basically, it changes where, it doesn't change where your graph hits the x-axis, but it changes where it hits the y-axis. So to give you kind of an illustration of what we're saying is that, let's say you have a quadratic that hits through here and here. Then if you have a certain A, then it may look like this and hit the y-axis here. But if you change your A, it's going to change the shape of the graph. Your x-intercepts are not going to change. It might widen the graph like this, which would change your y-intercept. Or you might even have it where it's, you know, really, really narrow now, like this, and then it would hit the y-axis way up here somewhere. Okay, how does the value of A affect the axis of symmetry? That doesn't change because everything I just drew, let me see if I can bring that back up. All of these would still all have the same axis of symmetry through here. So it does not change it at all. How does it affect the vertex? Well, it moves the vertex because if we have different scenarios here, our vertex can be in different places. So let me see. Is exactly 8 times the vertex. Okay, so it's the first part A, C, and D say it doesn't affect anything. So it's got to be B. What? Oh. The value, I didn't read these. The value of A does not affect the x coordinate of the vertex, but the y coordinate changes. That's true. So if I change A, the vertex moves up and down, but it doesn't move left or right. So it's got to be that one. Compare the x coordinate of the vertex with the midpoints of the x-intercepts. What might you conclude? So notice that the vertex is always the x coordinate. So if you just go up to these vertex, go right in the middle, you'll see that the x coordinate of the vertex is always right in the middle of these two x-intercepts. That's because of the symmetry. So the mean of the x-intercepts is equal to the x coordinate of the vertex. Mean half, mean opposite 2 times the mean, the average. And so that should be it. I wouldn't ask you these questions. Okay, which problem are we on? We almost done. Find the point on the line y equals xi. Hold on. Okay, for this one here, this is actually a pretty cool problem, but it's not that easy. It says find the point on the line y equals x that is closest to the point 2, 6. So let me draw you a picture of what we have here. We have the line y equals x, which we should recognize from our toolbox of functions. It's one of the important ones. And then we have the point 2, 6. So the point 2, 6, you go to the right 2, and you go up 6, wherever that is, okay, up here somewhere. And we're trying to find the point on the line that is closest to that. So we're trying to figure out, looks like the point that's closest would be somewhere around there. We're trying to figure out what point that is. So here's how we're going to do this. This is the point 2, 6. This is the point xy. We don't know what it is. So if I want to know what this distance is, right? Let's just figure out, first of all, what this distance is. And this point xy, since I don't know what it is, it could be anywhere, right? It could be here, it could be here, we don't know. So first, let's come up with a formula, d of x, which gives us the distance between those 2 points. Those 2 points, okay? Well, you have to know a distance formula. There's a formula that says that if you're given 2 points, x1, y1, and another point, x2, y2, that the distance between them is the square root of the x1 plus y1, sorry, I got that wrong, x2 minus x1 squared plus y2 minus y1 squared. So that is a formula we have to know going into this problem. So given 2 points, this will give us the distance between those. And so what we're going to do is we're going to come up with a formula for the distance between these 2 points. and then we're going to see where it's the smallest. So the distance for us between those 2 points is going to be the square root of, now I'm just going to replace the x1, y1, I'm going to make that the 2 and the 6. And the x2, y2, I'm going to make that the x and the y. All right, so if I replace and go into this formula, it will be x2, right? x2, which is x, minus x1, which is 2, squared, plus y2, which is y, minus y1, which is 6, and then squared. So this represents the distance between those 2 points. It could be this, it could be this, could be this. All right, so that's just a general formula. Now, very important point. Because this point here lies on this graph, the x coordinate will be x. The y coordinate, well, y is also x. So that point has to have the coordinate xx, which means I can replace this y in this formula with x also. So we get this. That's our distance. Now, the tricky part of this, if this hasn't been tricky enough, is that we would like to figure out when this is the smallest it can be. Because whenever this is as small as it can be would correspond to this blue point. So the way we do this is, it's hard to look at when the square root of something is the smallest it can be. So what we do is we square both sides, and that gets rid of the square root. And then we ask ourselves, when is this as small as it can be? So that's why they say here, find the minimum of d of x squared. So let's figure out when this question is, when is that as small as it can be? Well, this, if we expand this, we square this, we'll get x squared minus 4x plus 4. I'll trust that you could do the FOIL on that. X minus 2 times x minus 2, FOIL, and you get this. And then you say plus, now FOIL this one, you get x squared minus 12x plus 36. This is what d squared is. I still want to know when this is as small as it can be, but this is a quadratic. If I combine like terms, I get 2x squared. And if I combine the x's, I get minus 16x. And then the 4 and the 36, I get plus 40. So now I've got this thing that I'm trying to figure out when this is as small as it can be. But this by itself is a quadratic function. So if I graph it, it opens up because there's a 2. I know that the smallest it'll be will be the vertex, right? So I just need to find the vertex of this. So to get the vertex of that, I find h, which would be negative b, which would be 16 over 2 times 2. That gives me 4. And then k is what I get when I plug 4 into this. Okay, so we get, let's see, 16 times 2, 32 minus 16 times 4 is 64 plus 40. So I believe we get 8 here. So if we look at the vertex is 4, 8. So again, what we're saying is that this distance between these 2 points is dictated by this parabola, and the smallest it will be is when we're at the point 4, negative 8. So the smallest value we can get is when this is negative 8, right? And x is 4. So that means that x has to be 4 to give us the smallest value. So the point that we're looking at is the point when x is 4. Let's not lose sight of this. When x is 4 is when it's as small as it can be, but then that would mean y would have to be 4. So 4, 4. Go for it. Is that it? Okay, so we can talk more about that last one in class. Okay, so they give you basically a function here. It's a quadratic function, 1.1v plus 0.04v squared. They're talking about stopping distance of the vehicle on dry level concrete. So the first part says, how many feet will it take a car to stop traveling 45 miles per hour? So all we're going to do is plug in 45 into this and then get an answer. If an accident occurs 200 feet ahead of the vehicle, then what is the maximum speed that you can be traveling and not be involved in the accident? So the first question is saying, and I'm not going to do this, I'm just going to tell you what to do. The first question is saying, hey, just plug 45 into this function, figure out what you get. The second question says, hey, when would that distance be 200? And then they want you to solve for V. So this first one, I plug 1.1 times 45 plus 0.04 times 45 squared, and I would get some answer. This one, I take the original function and set it equal to 200. So that means you should move everything over to one side and then use your quadratic formula to solve. Okay, that should get you through most of this. I think I've given you a basic understanding of each problem, hopefully. The ones I didn't do these because we did a bunch of those in class. So I think you can handle this. If you can't, we can discuss any of these problems in class. Just let me know. Hope it helps.